Here we go. Last day, we introduced linear programming, right? Specifically maximizing and minimizing some objective function. And how do we do that? Usually we have some constraints that we're working with, right? And so it's a nice way to roll all the things that we've already learned into one kind of applied problem. And so this whole page is from last day, but I thought I could keep it because then I said, well, pick up here on Thursday. You can try it on your own. Maybe you did, maybe you didn't, doesn't matter. Right, but what we want to do, and I'll outline the steps once we finish this problem together, then I'll recap the steps because then we've got more optimization problems to work through. And so, but we'll follow the same procedure always. You know? So we had this problem. Oh yeah, Nikki holds 2 part-time jobs, job 1 and job 2, and she never wants to work more than a total of 12 hours. Okay, and so we had these constraints that we rewrote as linear functions, right? And so we had an objective function where if she makes $40 an hour at job 1 and $30 an hour at job 2, job 2, then how many hours should she work at each job to maximize her income, right? Which meant that we built this objective function, as we call it, where the income is 40 times x plus 30 times y. Now that looks like a linear function to me, and it is, right? And so we're trying to figure out what XY combination gives us the highest possible income given these constraints. Yeah? Before we were even able to do that, we had to decide what X and Y were, right? And so that's really kind of tricky. You want to identify the things that are mentioned in all the constraints, right? Because you want to build your constraints around X and Y, and also incorporate it into your objective function, right? And so that can be kind of tricky, and I just gave it to you casually, right? But in the next one, I'll make you work for it a little bit, give you some time to think about what to use as your X and what to use as your Y, right? I know I'm so tempted to force just the tiniest amount of group work on you. I know, impromptu group work, but especially for this type of problem, right? It's nice to kind of work it out together and kind of get there together, okay? So I know, not all the time, but sometimes, okay? Not for marks, so you're good. So we said, okay, we've got these constraints and we developed these last day, and we said, okay, she's not going to work more than 12 hours, and each job requires some number of prep for however many hours she's worked. And then we drew these constraints on one graph, right? Okay. So then these are inequalities. We talked about just briefly about inequalities last day, but you can figure out which side of the graph is going to satisfy the inequality, right? And so what we did here was we just took a test point, right? Just pick any point that you can see is in one of these regions, and if that test point satisfies the inequality, right? Let's focus on the X plus Y line first, right? If you draw a line at X plus Y is equal to 12, right? Then on that line, it's equal to 12, right? But you want to know which side of this line is it less than 12, right? And with practice, you'll know that it's just kind of below the line, but that's hard initially. So then if you pick a point, okay, if X is 1, Y is 5 in this just out of the blue point that I picked. Yeah. And then I test it. So that's why we call it a test point. I say, okay, x plus y. Well, x plus y would be 1 plus 5 in this case. 1 plus 5 is 6, which is less than or equal to 12. And so that's part of the area that I want, which means from this line here, right? This area, I'll remove this because it might be confusing. That area above the line is not satisfying the inequality, right? So you just want to use the area that satisfies the inequality. Okay, whoops. There. And then we did the same thing for the red line, right? 2x plus y, using the same test point as 7, which is less than 16, which was the constraint. And so then, and I did it kind of sloppy, I guess. Should clean this up. But this region here is your feasible set. All these xy coordinates in here can be solutions. They all solve this problem, but they're not all optimal, right? We want to find the best combinations of x and y. So all those xy combinations work, right? They satisfy all the constraints, but just as a fact, here's where we'll pick up today. Just as a fact, the objective function, which is the income in this case that we wanted to optimize, optimization meaning either maximize or minimize, depends on what you want to do. In this case, we want to maximize, right? But later we'll want to minimize, but the procedure is the same. So the objective function will be optimized at one of the vertices of the feasible set. At one of the vertices of the feasible set. I think they maybe I called it the feasible region or something like that. But just kind of the this region here. Which brings us to the next problem. We need to find the vertices. Vertices are just intersections, right? We know how to do that. If I ask you, hey, where's the intersection between x plus y is equal to 12 and 2x plus y is equal to 16, you know how to find that, right? Set them equal to each other, and away you go, right? And in terms of what you would be finding, that would be that point. I should point at it. This point here, right? The black line is x plus y is equal to 12, and the red line is 2x plus y is equal to 16. And so the intersection is this vertex here. Now, can I kind of, let's see here. I'm going to try to make it more obvious. Oops. Try to, I guess, is the operative word. It's not very good, is it? This is our feasible set. Feasible region. Usually what we do is we label all the vertices so that we can talk about them, just give them a name. A, B, C, D is pretty common. Using numbers might be confusing. You can if you want, but usually what we do is we start down here, call this A, and then I just move clockwise from the origin, from 0, 0, I move all the way around and I label all my vertices, C and D. The only one that's really going to give us grief, right, is C, right? That's going to be a little bit of work. Yeah. And so we need to find the vertices. Let's start with A. Nice and breezy. Just visually, I can see that A is at 0, 0. It's also because from our constraints, right, X had to be greater than or equal to 0 and Y had to be greater than or equal to 0, right? And so I know 0, 0 is one of my options. Not great for income though. Work 0 hours at job 1 and 0 hours at job 2. You're still satisfying all the criteria. 0 prep time, 0 work time. Cool. All right. But in terms of the income, it's not going to help you very much. So it's a bad solution. It is a solution, but it's a bad solution. How about B? Well, B is the intersection of which line? From here, it's the black line, which is X plus Y is equal to 12. And what? The y-axis is at X equals 0. And X equals 0. If I force X to be 0 here, right, 0 plus Y is equal to 12, then I know that B must be at X is 0 and Y is 12. Right. So then B is at 0, 12. Okay. C is the intersection of X plus Y is equal to 12 and 2X plus Y is equal to 16. Let me just confirm. 2X plus Y is equal to 16. Yeah. A couple of ways you can solve this. I'm going to rearrange both of these. You can use elimination if you want, but I'll use substitution and I'll rearrange both of these to be Y equals whatever, and then force them to be equal to each other. And so I can rearrange and say that Y is equal to 12 minus X and Y is equal to 16 minus 2X. This looks familiar-ish. Right, finding the intersection. And so if I force these to be equal to each other, right, then I can say 12 minus X is the same as 16 minus 2X at that point, right? Because they have to have the same Y value. So you can eliminate that middleman. Let's do this there. And now I can solve for X. If I move all my X's over to the left, I get negative X plus 2X is 16, and all my non-X's over to the right, 16 minus 12. Negative 1 plus 2 makes 1X, and 16 minus 12, I'm going to go for 4. We can check. In this case, we have the graph, and that looks reasonable. Right? And so, okay, X equals 4. When X equals 4, then Y should equal the same thing, right? Because we're forcing it to be the same, right? And so in the first one, Y is equal to 12 minus 4, I get 8 versus for Y is equal to 16 minus 2X. Y is 16 minus 2 times 4, 16 minus 8. I'll go with 8. So the intersection, after all that work, is at 4, 8. How about D? Oops. D is the intersection between which line? The red line, which is 2x plus y is equal to 16. And what's the equation for the x-axis? That's where y is equal to 0. Very similar to the y-axis. So if I force y to be 0, I get 2x is 16, which means x must be 8. Oops. 2x plus 0 equals 16, so x must be 8. And y must be 0. So then the intersection happens at 8, 0. Nice. So now we have all the intersections of the feasible set, right? The maximized income will happen at one of these 4 points, okay? And so that's the fundamental theorem of linear algebra. And so that's kind of cool. So usually what I do is I set it up as a table, right? And evaluate each of the points, right, in my objective function, because that's the thing I want to maximize. And so organized in a table. And I feel like A, B, C, D, just enough space. Bump this over here. I need one more line. And I want to keep it on the same page, so I'll bump that over here. So the vertex at A was 0, 0. At B, now I'm just summarizing it, was 0, 12. We already did all the work. At C was at 4, 8. And at D was at 8, 0. Now for the fun part. The objective function, and I'll use pink again, I, that we wanted to maximize, whoa, way back here, is 40x plus 30y. Right? And so what we've found are combinations of x and y, right? Different combinations of the numbers of hours that she should work at job 1 and at job 2, right? And so now we're going to plug all those in, and whichever one gives us the biggest thing, the maximized income, right? That's the one we choose. That's the combination that we choose. So now 40x plus 30y and we want to find the maximum. Okay. If x is 0 and y is 0, I get an income of 0. That checks out. If x is 0, let's show the work for this one, and y is 12, where's my trusty calculator? Oh my gosh, did I not bring it? Oh, I can't believe it. I feel naked without it. Okay. Use Desmos, the calculator. Oh, can I? Score. Okay. 40 times 0 plus 30 times 12 is 360. I'll just jot that down here. Kind of hard. For the next one, I've got, 30 times 4 plus, nope. You guys were just gonna let me do that, huh? 40 times 4. Plus 30 times 8. I'll do it all and then I'll screenshot it and bring it in. And then finally 80, 40 times 8 plus 30 times 0 is 320. It might click, but it didn't. Sometimes it's loud and sometimes it's not. That's weird. When I take that screenshot. Come on. Where can I do this? I'll put it over here. You were there. 360, 400, and 320. If I asked you which income would you like, which one would you choose? Probably C. Ta-da! You did it. Maximize your income, which means that you would work 4 hours at job 1 and 8 hours at job 2. Right? And that's how you would maximize your income. And maybe I'll do this. This is the maximum. You've got other options. They're reasonable, but 4 hours at job 1 and 8 hours at, I'll just go for 2, job 2. Nice. And that's the answer. A lot of little nitpicky things that you already know how to do, but now we're putting them all together. Yeah? So to summarize, right, the steps of an optimization problem. So here, the steps of an optimization problem look like this. First thing you have to do, well, the first thing you have to do, the very first thing is determine what X should be and what Y should be, right? So figure out what your variables are representing. Okay? And so pick X and Y from the question, right? And so it'll take some practice, right? Where you're kind of reading these questions, but as long as it's talking about the same thing over and over again in these constraints, right? Then you can use that as your X and Y. Pick X and Y from the question, right? Or kind of determine what X and Y are. Arguably one of the hardest parts, right, is trying to figure out, okay, what's going to make this all cohesive. 2 is identify the objective function, The objective function is the thing you want to maximize or minimize. Okay, and so identify the objective function. Right, the thing you want to maximize or minimize. The thing you want to, can I just write max or min? Max/min. The objective function has to be in terms of x and y, right? Because we're going to find x, y coordinates that would work, right? And so here, identify the objective function, I should have said, in terms of x and y. That's going to be kind of a clue, right? For figuring out if you can spot your objective function, right? Then you can use that to guide your x and y initially, right? So read the question through and figure out what you have and what you want to work with. And then you're going to list all the constraints, right? So then you'll list all the constraints in the problem, also in terms of x and y. Those are the things where she's not going to work more than 12 hours a week. No, no, no. She is okay working less, I guess, but no more. Right? So that would be a constraint that we have to consider. Next, you're going to graph the constraints on the same graph. Graph the constraints on the same graph. From those constraints, right, you'll find the region where all the constraints are satisfied. That's the feasible set. So 5, identify the feasible set, which is the region where all constraints, so it has to be all constraints are satisfied. Okay. Then what do? Then you have to find the vertices, right? Find the XY coordinates of all the corners of your feasible set. Find the vertices of the feasible set. Right. That involves some intersections of lines, which you know how to do. Right. Now, once we have the vertices, then we bring in the objective function, which we haven't touched, right? Beyond setting it up initially, we haven't touched it. It hasn't come into play at all. And so now you're going to evaluate the objective function at each of the vertices. The vertex that either maximizes or minimizes your objective function is the solution. I'll rephrase that. The solution is the vertex meaning one point, one corner, right? Vertices is plural of vertex. The solution is the vertex, which I'll say generically optimizes the objective function. Because it's true for either the maximum or the minimum, right? The rules are the same. It's just in the end, when you're evaluating which one you want, you don't want to maximize the cost, for example, you want to minimize the cost, right? And so then you want to pick the cost that's the lowest if that's your objective function. Okay. Now, how about another problem? Any questions though before we do? In groups, I know. You can do it on your own if you want, but it might be nice to chat a little bit. Try working through this problem. See what happens. I'm going to pause the recording because, wow, that would be so annoying. But I'm going to give you time to work on it, work through it, chat it out, and Zoom recording. A lot of time passed. And I wish we could do a time lapse in the classroom. Everyone's sitting on their own, and then I forced you together. Okay. Oh, I do see it. I do see it. There's a spider hanging down in the ceiling. Here. There you go. Love it. Step number 1, hardest part, right? Hate to say I told you so. Figuring out what your X and your Y is going to represent. Okay. What was one of the ways that it makes it a little bit easier is to first look at your objective function. You want to maximize the profit, you can kind of reverse engineer it because the profit has to rely on X and Y, right? And so whatever X and Y are talking about are going to be mentioned in this profit, right? And so the profit looks like this. How do I? Keep the spider out. It was just itty bitty. And it looked like it was like a white spider? Yeah. Like a yellow one? Ugh. For some reason that feels worse. It's all tropical. So your profit is going to be, you get 20 per regular gadget and you get 30 per premium gadget. And so if we just kind of start off here, we can use that as a clue to figure out what you should let your X be and what you should let your Y be. Okay? Because then, what if I let X be the number of regular gadgets? Oops. I almost spelled it with a J. That'd be weird. And I'm going to let Y be the number of premium gadgets. You guys have already worked through it, so you're going to be bored with me writing it all out. Usually, I'm sure it feels like I'm going so fast. Slow down. All right? Identify X and Y. You don't have to label them, but I want to match them up to the bullet points that I gave you earlier. Okay. Then you're gonna identify the objective function, which is the profit function. So the profit in terms of x and y is going to be 20x plus 30y. And then we parking lot that forever, right? We don't incorporate it really until the very end. Okay. Oh, these constraints. Right? It's this little tiny bullet, but it's a lot of work. Right? So, first things first. You want to have, so each of your constraints should have an X or a Y, or preferably both, right? If you have information on both. And so your constraints in this case, I would break it up, and this is kind of, going to come with practice, right? But if we have 12 hours at most for assembly and then finishing, right, each, then a regular gadget, so the number of regular gadgets is X, requires 1 hour of assembly. And if I just focus on the assembly, for the premium gadget, I need 2 hours of assembly. Right? And so now, if I kind of break up these constraints, like so, I could have an assembly constraint, or like that, an assembly constraint, which said, okay, 1x plus 2y has to be less than or equal to 12, right? That's the amount of time that it takes, right? It can't take more than 12 hours. You don't have to write the 1. Just want to emphasize that it's just 1 hour. And then we have the same sort of constraint on the finishing time. Oops. But we add a regular gadget requires 2 hours of finishing, and a premium only requires 1 hour of finishing. So then we have 2x plus 1y, and we're still limited to 12 hours per week. Or I guess it's not necessarily per week, per day maybe. 12 hours, that seems reasonable, in a day. And then they snuck another one in. That one's easy to forget. But due to other restrictions, the company can make at most 7 gadgets a day. So the total number of gadgets has to be less than or equal to 7. Right? And so here, the total gadgets, x plus y, has to be less than or equal to 7. Right? So you could play around with it, right? Because the number of gadgets is a whole number. In theory, you could list all your x's from 0 to 7 and the corresponding y's, because they can be at most 7. That's kind of brute forcing it, right? You don't want to rely on that, but you could get to the answer that way. What's another thing? I can't produce a negative number of gadgets, right? And this one is just to make our job a little bit easier, right? And so must produce a positive number of gadgets. Which means x has to be greater than or equal to 0, and y has to be greater than or equal to 0. Right. That's how you force, even if you didn't list those constraints, right, you probably applied them when you looked at your graph, right, and said, oh, I ignore that, right? But then you want to list them. Yeah? Okay. That's listing your constraints. That's a lot. Okay. And let's see here. graph the constraints on the same graph. So you can ignore the inequalities if you want to, but if it's less than, right, all of these are less than, then you're going to be kind of below the line. For me, that's kind of difficult to think about, right? Luckily for us in Desmos, it'll graph it, but to save you some time on the test, I'm not going to make you graph a line because that's difficult, right? And kind of annoying and nitpicky, right? And so then I would give you the lines and it would look a little something like if I made it equal to instead. Equal to. I would give you a graph like this. Let's do it that way. But I wouldn't give you the legend, would I? That would make it too easy, I think. I would give you maybe something like this. I'll call this line 1, line 2, and line 3. Without knowing the equations, right, then you need to map these lines back to your constraints, right? And so you've got your constraints. Should we deal with x greater than 0, y greater than 0? I already kind of did in my crop here, right? But I need to be above this line, and I need to be to the right of this line, right? Is it that time already? Yeah. Okay, pick up the pace. Okay, now we're almost there. We are? I know, we are. So now, let's figure out, let's kind of reverse engineer it. So instead of having you draw the graph, unless you prefer to draw the graph, you can think about it. I'll take requests closer to the test. But let's reverse engineer it and say line 1, I didn't even give you the y-intercept. I should have. That was an oversight on my part. Should have taken you all the way up there. That's okay. It's not part of the feasible set. That's why I cropped it. But the line where x plus 2y is equal to 12, right? And so if I pick some points on this line, let's maybe pick some obvious points like here. Oh, sorry. I'm doing this blue line first. Let's do here. I see that it goes through 6, 0. Right? I see that it goes through, well, that one's actually kind of tricky because what's my x there? Looks like it's 5, 5, 2. Yeah. And so here, line 1 goes through 6, 0 and 5, 2. From working through your assignments, that looks really familiar, right? You know how to find the slope of this thing, right? And then you can map it back, right? And so let's do that. y2 minus y1 is x2 minus x1. The slope of this thing is going to be 2 minus 0 divided by 5 minus 6, putting me at -2. Which of those constraints had a slope of -2? I think the easiest to rearrange these in terms of y equals mx plus b if you have to reverse engineer it. right? If you don't, if you're just drawing them, then you can just use them as is, right? Pick a value of x, solve for y, find that point, plot that point, right? But just as an aside here, this would be the same as y equals 12 minus x over 2, which has a slope of what? -1/2. This next one, if I solve for y, and replace the inequality with an equal sign, I get 12 minus 2x. Hey, that looks good. That's the slope I wanted. I had a slope of -2. And then here I get y is 7 minus x. Oops, run those all together. So if I rearrange them, then all I really need is the slope of each of the lines, and then I can map them back, right? And so here, the slope of line 1 is -2, which means that this is going to be line 1. Right? And I find it's easier if I just draw it on here. So line 1 is 12 minus, or let's do, I've already solved it for y. Let's keep it that way. Y is 12 minus 2x for line 1. Can do the same thing for line 2, but if you had to pick, right? This first one has a slope of -1/2, and this next one has a slope of -1, but also the y-intercept is kind of telling, right? 12 divided by 2 is a y-intercept of 6, which tells me from here that that must be the red line, right? So you can kind of reverse engineer it, right? And so, and that's all I want you to do. Doesn't matter how you want to solve it. So the red line is line 3, which by elimination, line 2 is the last one, or the middle one. No, the last one. Line 2. So if we jot these down, line 2 is at y equals 7 minus x. And line 3 is at y equals 6 minus 1/2 times x. If you break up that fraction into a y equals mx plus b type of situation. Okay. Why do we need to know the equations of the lines? So we need to find the intersections of some of these. Okay. Now the feasible set, starting out here at 0, 0, all of these lines, so we have to be less than these, right? And so all of these kind of go down from all the lines, has to be below, below, below all these lines. Okay. So from 0, 0, you can only spread out until you hit a line, right? Because it has to be less than that. For minimization problems, it's a little bit more work, because usually then your feasible set is kind of this region, this kind of region. We'll look at minimization next day. So from here, right, if I draw my feasible set here, goes from here to here to here to here to here, and everything inside there. All those XY coordinates are solutions. Not optimal, but solutions. Okay. We kind of did something different, right? Graph the constraints on the same graph. I gave you the graph in this case, because it's easier than drawing them all. And then you have to figure out which line is which. Okay. Identify the feasible set, right? We did that. Just that little area. So that was 5, I guess. There. Put it there. Put her there. Find the vertices of the feasible set. Right? A lot of these are kind of a little bit easy, right? Y-intercept, X-intercept, for example, but you're going to label each of these vertices. Let's call it A, B, C, D, and E. Starting at 0, 0, and then working around clockwise. Right? And you don't want to forget any. And then I did give you the vertices, but let's do the work for finding them, because that's what's more important to me, right? Is that you're able to find what those intersections are, right? And so I guess 6, find the vertices. A is kind of a gimme, 0, 0. B is technically the intersection between y equals 6 minus 1/2 x at x equals 0, right? So it's technically an intersection. You can see it clear as day, but let's see, let's write it out. The intersection of y equals 6 minus 1/2 times x and x equals 0. Right? The y-intercept is at x equals 0. If you plug in x equals 0, you get y equals 6. Right? And so kind of a breezy point to find at 0, 6. For C, C is the intersection of, let's be real careful here, of the red line and the green line. Yeah. So C is the intersection of the same line of y equals 6 minus 1/2 times x and the green line, which is at y equals 7 minus x. It is useful that I've rearranged them all in terms of y equals, y equals, y equals, right? You don't have to, but you will eventually. 7 minus x. Because now finding the intersection, I can just smush them together, right, and solve for x, and then use that to solve for my y. So I get 6 minus 1/2 x is equal to 7 minus x. If I collect all my x's on one side, I get negative 1/2 x plus x is 7 minus 6. Negative 1/2 plus 1 puts me at 1/2. 1/2 x is equal to 1, which means that x must be 2. 2 over 2 is 1. Can confirm it. Looks perfectly reasonable. Right. So now let's figure out what the y value is at x equals 2. Let's use 7. Y is equal to 7 minus x. Right. So here, y is 7 minus x. So y must be 5. Putting this point at 2, 5. And I'm going a little bit faster, probably, than I should be. Just so we can cover it all. The next hard intersection is D. E is a little bit easier. D is the intersection between the the blue line and the green line. Intersection of y equals 7 minus x, oops, and y equals 12 minus 2x. Setting these equal to each other. To find the intersection, I get 7 minus x is 12 minus 2x. Move my x's to one side, move the 7 over to the other side. I get negative x plus 2x is 12 minus 7. Uh-oh, 12 minus 7 is 5? Nice. And negative 1 plus 2 puts me at just x. X is equal to 5. Using either of these, we should get the same value of y, right? If I use y is 7 minus x at x equals 5, y must be 2. So then the point is at 5, 2. And then finally, E is the intersection of which? The blue line, 12 minus 2x. And y equals 0. Which means that 0 is 12 minus 2x. Solving for x, I get 2x is equal to 12, so x must be 6. Putting my point at 6, 0. Which then, my next thing, find the vertices, and then we make a table of the vertices. A, B, C, I know. D, E. Listing all these, I've got 0, 0. B is 0, 6. Was it 5, 2, 5, and 5, 2? Convenient. And 6, 0. Whew. That was our goal, sort of. We still want to maximize the profit. The profit, that's when we bring it back in. It's been a while, is 20x plus 30y. If x is 0 and y is 0, I get 0 profit. That's probably bad. I don't want that. If x is 0 and y is 6, I get 30 times 6, right? 2 times 0 plus 30 times 6, which I could be wrong. Could be 180. Yeah, thank you. How about 20 times 2 plus 30 times 5? 40 plus 150, 190? Only because I've already seen it. I know it's 190 is the answer, so I know it's out there somewhere. 20 times 5 plus 30 times 2. Oh, the math. 100 plus 60, 160. Okay, it wasn't that bad. 20 times 6 plus 30 times 0, 120. If you're choosing between all these profits, you choose 6, 0 because it's easier. No. You choose, oh, whoops. Oh, pink. This is the maximized profit, producing 2 regular items and 5 premium items. Therefore, the profit is maximized at $190, let's assume, producing 2 regular and 5 premium gadgets. Step away from the plate. You did it. We did it. Good job. We've got more of these for next week. Ah. I usually give you at least a week to do it from the time that we kind of finish it. So I think, yeah, I'll do the maximization homework a week from now. See ya. And then the minimization later. Tuesday. It's the same. You're just trying to, yeah, usually the constraints go on the upper end. And then it's the same. That's okay.
Thank you.